Okay, hello, good morning. So today we're going to start off by looking at the chain rule. And so what's behind this is the question of how do we differentiate? Remember that word means how do we measure the instantaneous rate of change composed, aka chain functions. So this is, you might have seen this as f follows g of x with this composition operation between functions, or f of g of x is very common as well. So if I have a function within a function, how do we deal with that, right? We've looked at sums, we've looked at products and quotients of functions, but what if I have a function plugged into one another? And this is a huge outcome of the course. And so we're going to spend a lot of time on this particular rule because of its importance and its applications. So first we'll look at an intuitive example, which will be very simple, but to drive the point, which obviously becomes more complicated depending on the context. So intuition, then we'll look at the definition of it. And then we'll do one applied problem. All right, so let's take a peek. Okay, so here I've put myself up against my brother in a race. So let's try to keep as basic a perspective as possible. So let's say I'm running 8 feet per second, and my brother can run 1.5 times as fast as me. I don't know how he does it, but man, he's just always 1.5 times faster than me. So the question is, how fast is Chris running? So you might be able to very simply do the arithmetic and solve this problem. That's not the point. The point is to really think about this from the calculus perspective and from a perspective of chain functions. So you'll notice that his rate doesn't care about time. It only depends on how fast I'm running. So if I changed my rate, he would obviously go faster, right? Or if I slowed down, he'd only go 1.5 times as fast. So it only depends and scales with mine. So his input, really, for his position function is whatever my speed is. So one way to view this is Sean's position is given by 8t, where t is in seconds. And then Chris, he's 1.5 times as fast as me, so he's going 1.5 times as far. Okay, so he's just taking that 1.5 times my position. So you can view this as Chris's position is a function of my position, right? He's going 1.5 times as far. So another way to put this into calculus terms is that ds dt, my rate of change, is 8, and you can think of this as feet per second. And Chris's rate of change, dc ds, right, since his position is a function of s, is 1.5, right, the derivative with respect to x. That's the scale factor. So then one way to think about the question, how fast is Chris running? Well, this is relating his position to time, right? That's your rate or your velocity. So that's his distance, so you can think of this as being in feet per second. So that would be dc dt, Chris's rate of change with respect to time, not with respect to how fast I'm running. So you can think about this in a rate relationship like this, as taking dc ds, which has really no units. It's really kind of feet per feet, if you think about it. So it's just a scale factor, but it's dc ds times ds dt, how fast I'm running. And so that'd give us the 1.5 times 8, which gives us 12 feet per second. And one way to kind of make this work in your brain a little bit is if you think of this as two fractions, which we're kind of waving our hands a little bit and doing some fuzzy math, which is okay, because the intuition is good. That what do we see? Oh, the ds's kind of cancel, and you're left with dc, which has the units of feet per second dt. So that's how we maintain those feet per second here. So the one thing I just really wanted to highlight here are these two ideas. Is that finding the rate of a composed function is really the product, the scale of the two functions themselves, but you'll note that they keep their same inputs. Okay, so C only depends on S and S only depends on T, but the rates do simplify in this way, and that's what kind of preserves the rule and preserves our units and keeps them all in the right spot. Okay, so here Chris's speed is changing with respect to how fast I'm running, and I'm running with respect to time. So each of these things are respected. So, we've got input 1 and input 2. So let's think a little bit graphically about this now. Why does the rate of change scale? I mean, with that example, it was easy because we know he's always running 1.5 times as fast, so that's necessarily going to scale. But if we think about taking this as a chain of functions, right? What happens when we have f of g of x is my, output y? Well, we've got my input x is here, and when I wiggle that x, it's going to affect g in some way, right? Because g is a rule that depends on x, and it has an output. And if we feed that output to f, now f is going to wiggle in some way, and that will lead me to my output of y, right? So you can kind of think of this as a chain, and if you have your hand on the end of the chain and there's a few links and you wiggle it, you know how one will wiggle, the next one will wiggle, the next one. It's the same exact idea. And how much you do that depends on, the physics of the situation, how each link is connected. So, dx is really that wiggle, that infinitesimal nudge, the limit as we take that time wrapper to 0, as we did with the limit definition. That wiggle in x is going to produce some wiggle in the output g. That will produce some wiggle in the output f. And so y is going to be the combination of these two wiggles, right? They're going to kind of amplify or scale each other. Okay, so if we want to think about how y is changing with respect to x, then we need to know that, well, y is the output of f. So we can think of this as df, but f changes with respect to what? With respect to g. And g is going to be changed by x itself. So f changes by g, and that change is scaled by its relationship to x. So now here we see that same thing we saw last time, which is this df dx. Okay, so this is the big piece to take away, is that this change is scaled through the chain. Okay, so when we come to chain functions in general, how is this going to look? If I have y equals f of g of x, then y prime of x is equal to f prime evaluated at g times g prime of x. Another way to think about this is this df dg times dg dx, say aka. So, it might take you a second to wrap your head around the difference in notation here. This is the first time you've probably seen this guy. So what this really means is this is the rate of change of f, but evaluated at g. Okay, so ultimately it has an input of x, but its intermediate variable is this g. So we want to make sure that we note that the input is g here. Okay, so that whole function, because that's what f eats as its input, right? It eats g. So here, for example, sine of x cubed, we would call f of x sine, and g of x we'd call x cubed. And so, our y at the end of the day is f of g of x, which is sine of x cubed. So you see how f is eating this x cubed function here. And so that's how we would differentiate here. So to just finish this example, what would f prime then be? Or what would y prime be? Y prime then is f prime at g of x times g prime of x. Well, f prime at g of x, what's f prime? F prime is cos x, but it's evaluated at g of x. So f prime here is then cosine of x cubed, right? Because that's my g of x, times that inner rate of change, which we want to know what g prime is. Well, we know that's 3x squared. So that's times 3x squared. And then I just simply simplify this to be, we typically would write it like this. So that's a formula for y prime. Now we're going to do a couple more examples here, but I wanted to just finish this one real quick. But before we do that, a few pro tips, which is you need to start seeing these functions with chunks or hidden brackets or outer and inner functions, which is usually how I describe it in pre-calc. But to start to see things as chunks, so, right, 3x plus 1, that's a chunk, that's a linear function that's being fed as an input to f. Here, sine of 18e to the x, you see these brackets, it's kind of treating this as a blob, right? This is one input. Same thing here, e to the sine 2x. What is the outermost function? It's really e to the something, right? And that something here is sine 2x. For 2x minus 4 to the 8th, I want you to start seeing this as something to the 8th. And you'll notice where these brackets are is defining what that chunk is. And then this last one, what is this? The outermost function is a square root, so you could really think of this as square root of something. But then the inside would be, I have another chunk. I have sine with sine of something, right? And so that is that second chunk. So to start to see these things as like those nested, those nested egg dolls, those Russian nesting dolls where you pull one out and there's another smaller one inside. And we're talking about this all the way down, where the end of the road is x or t, depending on whatever your independent variable is. And you'll see what I mean through your practice examples about that. But, once you get to x or t, then you can stop treating them as chain functions. So we're breaking these things down into their smallest Lego blocks, and these might also have inner chunks themselves. And I'm using this very informal language because I want to appeal to the intuitive nature of this thing instead of all the math jargon, which will just, come on its own. So we're breaking them down to their smallest Lego blocks, and to know that the Lego blocks really come in this unit of these blobs or these chunks inside brackets. Okay, so I think you should take a moment here and pause this video and just make sure you see for yourself what I'm talking about here as treating these inputs as blobs or chunks. And so then let's do one kind of applied example here. This comes actually from differential equations, where we can have something called a damped sine wave or damped cosine wave, where the oscillation is decaying over time. And so let's say a car crashes into a building's wall, and the reverberation in the structure can be modeled with a damped oscillation. So here's some parameters for this. So we'll say this is in, that y is in inches at t seconds. All right, now I have made up these parameters to make this a simpler problem. These would not be realistic, but the form of this function is very realistic. But the numbers are not. Okay, so if we get to the end and it doesn't really make any sense, that's okay. The whole situation is actually quite realistic. So find y prime and explain its meaning. So y prime, all right, is going to involve the outer and inner functions. Now, you'll notice that at the outset, we have actually a product of two functions, which you should be familiar with at this point. You've got we could call it 5e to the negative 2t, and you've got a cos of 2 pi t. So you've got an exponential function and a cosine function. All right, and we've differentiated something like this before, but never with an interior function themselves. So we got to break this down, and so this is going to be a little more complicated than your standard chain rule question, but I wanted to do one that was significantly more difficult to model it for you guys. So y prime then is going to, if I treat this like my f and this like my g, all the rules should still hold up, right? So the product rule is the outermost kind of operation here. We have a product of two functions. So it should be, you know, f prime g plus f g prime. That should hold up in our product rule. So the question is then, what is f prime and what is g prime? Well, if f is 5e to the minus 2t, f prime is, well, it's that outer chunk. So it's 5e to the minus 2t. Oops. It's 5e to the minus 2t. What's the derivative of that? Well, the derivative of 5e to the something is 5e to the something. But then times the derivative of that something, right? The inner derivative. So what's the inner derivative here? All right, so this is, and circling that inner function can be very helpful, especially when you're starting off. So circle that inner function. So 5e to the something becomes my outer derivative times the inner derivative, which we know is minus 2, because that's just a linear function. Right, so the derivative inside is just minus 2. So all day we get negative 10 e to the minus 2t as my f prime. And so let's do the same thing for g. If we said g is cos 2 pi t, then what's g prime? Well, again, let's circle that inner function. We'll say this is my inner function, so that outside, that means that my function is a cosine that I'm differentiating. So that should leave me with negative sine on the outside, evaluated still at 2 pi t. Remember that inner function doesn't change here, but I need to scale it by the derivative of the inside, which is what? Derivative of 2 pi t. Again, that's a linear function, so that's going to be 2 pi in here. Okay. They're not always linear inside. Okay, you could have a parabola or another cosine, whatever. It doesn't quite matter. I'm keeping this one a little simpler. But it is whatever the derivative is of the inside. This is that nesting doll kind of graphic you can think of. All right, so then I can go ahead and write this out. So f prime we said was negative 10 e to the minus 2t times g, which g is just cos 2 pi t, plus f, which we said was 5e to the minus 2t, times g prime, which is negative sine 2 pi t times 2 pi. All right, and so we could simplify this just a little bit. One way you'll see it often is that they'll pull out the e to the minus 2t, and I'll actually do that here. So we'll pull out a factor of e to the minus 2t, and we'll be left with negative 10 cos 2 pi t. And then I'll combine the scalars here. So I have a scalar of 5 and 2 pi and a negative. So this will be negative 10 pi sine 2t, 2 pi t. And you could also pull out a factor of negative 10 here. I'm not going to. mainly because I'm out of room. But this would be the derivative for this function. And you see maybe the two rules in action looking at it all the way at the end of the road, right? You see there was a product, so we used the product rule. But there was also, each of these was a chain function, so we used the chain rule twice. Okay. So now we found this. Very cool. What is the meaning of this thing? Well, if y is the inches in displacement, right, the reverberation of this wall, and t is in seconds, then this gives us, right, the speed of the reverberation. Or the oscillation. Right? It gives us that speed in feet per second. Or you could think of it as the velocity of it, because it's going to tell you the direction as it wobbles. You know, if that was the worst car in the world. And this is not much better. But if this crashes into the wall, and this thing starts to wobble, we're talking about dy dt is the speed at which it's wobbling back and forth. And again, if you look at a graph of this thing, which I'll show you quickly. So this is the displacement of the wall. Again, it's decaying over time because it stabilizes itself. And then what would we expect the derivative to look like? Well, it's going to be sine function, so it's kind of inverted from this, right? It's got a little bit more of a bounce because of that added piece. But as well, it also decays over time, and as the wall stops moving, then that speed, right, the rate at which it's moving also is decaying, and so you see them both kind of tend towards zero. So it's just a little physical application there. But the main thing I wanted to do was combine the rules that we've learned so far. And again, using this definition here of the chain rule, and maybe let's close with just writing that out completely explicitly, what the chain rule really is. So if I have y as a function of g of x, a chain function, y prime is f prime of g of x times g prime of x. Remember that pro tip of always circling that inner function, because that will remind you to evaluate the derivative at that inner function. So I'm going to do one more quick example just to drive this home. So if y equals cosine of 13x squared, maybe you can hit pause and try to apply this real quick. So I circle my inner function. Derivative of the outer function is negative sine. That's being evaluated at the inner function, 13x squared. And then it has to be scaled by that inner rate of change, right? Just like my brother was running 1.5 times faster than me. How much faster or slower is the inner function moving with relation to the outer function? And so the derivative of the inner function is what? Well, 13x squared, the derivative of that is just a power rule. It becomes 26x. Okay, and whenever there's simplification that can be done, go ahead and do it. So like here, bringing out your scalars to the front, things like that, you know, combining negative signs, all that. But I hope this helps highlight the key points of the chain rule for you. You will be now mixing this in with all the other rules you've learned. Again, sums, differences, products, quotients, and now chaining functions together and how they all change. And, you know, again, when we set forth our definitions in this way, what must be the case afterwards? That's kind of the experiment you're running with all the functions we've learned about. So hope to see you in the class discussion. Enjoy. We'll see you next time.